So let's move on to Lecture 8. This one will be a shorter lecture, being that Lecture 7 had quite a bit of new information. So for Lecture 8, we're looking at problem solving for all types of energy questions, and then we'll do a brief explanation on power. So how are we going to deal with conserved and non-conservative conserved problems? So we've had a couple of these topics brought up, but how exactly are we dealing with them? Well, problems can be made easier or more difficult with different approaches, right? So on some problems you're going to want to use the kinematic equations. On other problems it might be easier to look at energy as your focus for solving out problems. There's some tricks that you can use when the forces are all conservative. So if you have something that doesn't depend on friction or any type of resistive forces, then everything must be conservative, and you can apply a conservation of energy equation into the problem, which means it's kind of like an equilibrium. It means that the total change in energy must be zero, and if the total change in energy is zero, you can add up all of your energies, whichever they may be. They could be the kinetic, they could be gravitational potential, it could be spring potential, but the total amount of energy doesn't change. So total amount, the change in energy be zero, and you can use it like an equilibrium equation to solve for what you need. If you have problems that do not have conservative forces, so non-conservative forces, they're just a little bit more difficult, but you need to just look at where is that non-recoverable energy, where did it go, and why. So in this case, the change in energy is not zero, but is in fact the energy that you lost, right? So you might have a problem, where energy was taking place, but some of it was lost due to friction, in which case you can still use the change in E equation, list out all of your different energies, but you'll see that the energy lost, it's not going to be zero. You will have an energy that is lost, and from that you can then go and figure out what the hopefully what the friction force was, or resistive force, or whatever it happens to be. Okay. All right, small dive into power. Power refers to this relationship of energy and time. The more energy you put into a system in the shorter amount of time, the more power that you can deliver out of it. So the equation for power would be a capital P for power, and it's the change in energy over the change in time. So in a derivative term, it's dE over dt, the change in energy over the change in time. Okay. We have a couple of different ways that we can formulate this equation, and we can use a little bit of algebra to get a different view of it, to just arrange it differently. I know, so that put that in there twice. We gained it in the last few chapters, and we arranged it differently. Anyway, if change in energy is just the same as work, we can actually look at work over time. Okay, well, work is just force multiplied by a distance, right? So work is force times a distance divided by time. Well, distance divided by time is a velocity. So really, power, we can use it as the change in energy over the change in time, or we can look at it as a force multiplied by a velocity. Okay, how fast it is moving. So the SI unit here for power would be energy over time, so you would get joules per second. It's more commonly known as a watt, even though it's not an SI unit for power, but it is more commonly known as a watt. There are a couple of different ways of writing watt. In the US, we don't refer to watt for most things. We refer to it as horsepower. So there's an easy conversion that we use here to go from horsepower to watts. It's an odd number, but 1 horsepower, which is abbreviated as HP, is equal to 746 watts, which is a capital W. So this takes you all the way back to chapter 1 to do unit conversions, but you could change horsepower into watts. Now, if you've ever paid an electric bill, likely you were paying per kilowatt hour amount of energy that you used. But we saw watts as in unit of power. So how do we pay for energy? Well, the kilowatt hour represents energy in terms of power. It goes back and forth. Just so you know, I mean, a kilowatt hour is a very common thing to see. It's the amount of energy that is transferred in 1 hour's time at a constant rate of 1,000 watts. Now, you might not, powering your house or using your microwave or whatever you're doing, you most likely won't use 1,000 watts in every hour, but this is how it's billed, right? It's the amount of energy that refers to this amount, 1 hour's time of 1,000 watts. So 1 kilowatt hour is 1 kilowatt, so 1,000 watts, or 10 to the third watts, and an hour being 3,600 seconds means that the amount of energy that you use, 1 kilowatt hour, would be 3.6 times 10 to the 6 joules. Okay, so in an average month, how much energy do you use on your house, or your apartment, or your parents' house, or whatever you have going on there? The amount of joules of energy that you use will be represented by how many kilowatt hours that is equal to. So it's just another conversion. Okay. So we'll do some problems on kilowatt hours. We'll do some problems on horsepower. We'll do problems on power. And we'll do lots of problems on conservation of energy, having the energy be the same. All right, so this is a pretty short video. We can go ahead and just stop here and let's go to the board and get some problems in. All right, so we'll start chapter 8. First example here, we're dealing with energy conservation. So we have 3 types of energy, which we've talked about in the last chapter: kinetic, gravitational potential, and spring potential. Conservation of energy allows us to just do a much wider span of problems and solutions and things. So we just need to ask ourselves a couple of questions before we begin a problem so that we can figure out how to best solve it. All right, so this example here, if I were to write this out in word form, it's really, really long, and a picture is always best anyway. But what the word problem states is that you have this soft air pop gun thing that has a little plastic BB or projectile in it that weighs 35 grams. That's not an SI unit, so go ahead and convert that right away to 0.035 kilograms. It's loaded into a spring type kind of a gun, and it's compressed down. So the amount it's compressed is 0.12 meters. So this is kind of like the loaded area here. From y equals 0, we compress it down 0.12 meters, and it's held by a trigger. When we pull the trigger on the little pop gun, it releases the BB. The BB then flies out, and it travels vertically a height of 20 meters before it stops. So this is the velocity of 0. It turns around and falls back down. So that's the premise of the problem. Part A asks us, what is that K constant? It's asking the K constant of the spring. Part B says, what velocity does the ball pass y equals 0? So it initially had to leave the gun with some velocity. What was that velocity? Okay, so similar to some of the problems we did in the last chapter, but this time we can ask ourselves a couple questions and do them a little bit easier. We have multiple energies going on. We have a height change that's going on. We have a spring that's being compressed. We have questions asking for velocity. So we have lots of energy questions happening. And the first one that we want to ask ourselves for questions is there any friction, right? Is there any resistive forces that are going to prevent that energy from being conserved? And in this one, it doesn't state anywhere that there's a mu. It doesn't state that there's air resistance. the actual word problem itself said to go ahead and neglect all of that it's not happening. So we're going to go ahead and say that there is no friction. Energy here should be conserved. If the energy is conserved, it means that the final energy is equal to the initial energy. So final equal to initial. Now that we know that the energies are equal, all we have to do is ask ourselves, pull that down just a little bit. All we have to do now is ask ourselves, what types of energies are in which part? So what energies are in the end, in the final state? What energies are in the initial state? So I'm going to write a couple of these out because I've got them over here. And I'm going to ask myself these questions. In the final state, when the ball is up here, do we have any kinetic energy? Okay. Kinetic energy would mean that there's a velocity in the end. That velocity we know is zero because it's stated in the problem. That velocity at the end point is zero. So there is no kinetic energy. So I'm not even going to write that one down. No kinetic energy. Is there a y value? So that's the gravitational. Is there a y value in the end of the problem? Yes. The y value now is at 20 meters. So I have to include that one. If I were to write all these out, this is usually how I would do it. I would say kinetic energy plus gravitational plus spring is equal to kinetic energy plus gravitational plus spring. Okay, and then it lists all my energies. Now I know this one is zero. Kinetic energy is zero. But gravitational energy stays in, which is going to be mg y final. Because we're in the final side of energy. Now I go spring. Do I have spring energy when the ball is up here? And the answer there is no. So when the ball is up here, there's nothing compressing the spring anymore. There's no more kinetic or no more spring energy to have. So that one is also a zero, which just leaves me with mg y final. Now I look at the other side of the equation. Everything has to balance. In the beginning, when the ball is down here and it's compressed, do I have any kinetic energy? Well, no. We're not at part B yet. We're just in part A. So if the ball is down here and it's compressed, I don't have any kinetic energy. The ball, again, is not moving. It hasn't been released yet. So that's going to go to zero. Is there a y for the gravitational energy? Is there a y value? And that is yes. We have a value here. So this is going to be mg y initial. Okay. And then we ask ourselves, well, is there a spring involved in the beginning? In the initial, is there a spring involved? And yes, of course there is. We now have a spring that is compressed. Okay, so that's going to be 1/2 x squared. So there's my k that I'm looking for, 1/2 kx squared. The k is the thing that I'm looking for. That's what question part A is. Okay, so now I can start putting some numbers in and see where we go. The mass is going to be referring again to the mass of the ball. So we've got 0.035. Gravity is always 9.8. G is always going to be 9.8. Y final, it tells me that it's 20 meters. 20 in there. Equals, again, mass, 0.035. G, again, 9.8. Y initial. Y initial is 0.12, but be careful. 0.0 or 0.12 is below y0, so this is a negative 0.12. Okay. And then this is plus 1/2 our k, which is the thing that we're looking for, and x squared. X would be the negative 0.12, but it gets squared. Okay. All right, let's see what we can do with that. These energy problems, they get really long. They get really, really, really big. It kind of triangles out, but then it narrows back down again and gives you a nice, concise answer. So I actually enjoy working with these ones. So I'm just going to see what this first value is. The 0.035 times 9.8 times 20. This number here gives us a 6.86. That's going to be equal to 0.035 times 9.8 times a negative 2. So this will give us a negative 0.04. Okay, for the second part, right? And let's see, plus 1/2. I can take 1/2 times the negative 0.12 squared, and that will give me k times 0.0072. Okay, so hopefully that made okay sense. This is just here. This is here. This is here, right? So I'm just doing some math, getting some basic stuff there. So what I want to do now is keep going on the algebra. I'm going to add that 0.04 to the other side. That'll give me a 6.87. And then I'm going to do a division, right? 6.87 divided by that 0.0072 gives me a K constant of, let's call it 954. And then again, if you have to think about what your units are for the K factor, go back to the equations for spring and grab them from there. Or you can do it in energy if you want. You could have joules per meter squared, same thing. Just make sure you do have units on your answers. So K constant, there we go. 954. Let me go ahead and add that over here. Okay, there's our answer for part A. Hopefully that made okay sense. I wanted to use the 2 points, the end point and the initial point, at the very top and at the very bottom, because that involved the spring. I was looking for the K constant. I wanted to pick those points to use as my reference, my final and my initial. For part B, I want to switch that up. I want to change the points that I look at. Okay. So for part B, let me erase this over here now that we're done with it. For you, you can just start over again on a separate line on your paper or whatever you're taking notes on or whatever it is, doesn't matter. I'm actually going to just take it all out because I messed up there. Okay, so again, I'm going to start with energy. I have different ways of looking at it, but now I want to again compare where I am and what energies I have at those points. So I'm going to write out all my energies and I'm going to ask myself the questions again. The final point, being it wants to know the velocity of the ball at 0, I'm going to use that as my final point. And I will use the compressed state as my initial point. Okay, so in the final, this time, I'm looking at the y equal to 0 line. Does it have kinetic energy at the y equals 0 line? The answer is yes, of course it does, because the ball has just been released from the spring. It will have 1/2 mv final squared for energy, and that is the velocity that the question is asking for. Okay. Does it have gravitational potential at that point? So I'm looking for the y value. Does it have a y value? It has a y, but it's 0, which means it will have no gravitational potential energy at that point. All right, next I ask, is there a spring energy at the point of y equals 0? Okay. Similarly, spring energy is 1/2 kx squared. The x squared refers to how much the spring is displaced. At y equal to 0, the spring is not displaced. X would be 0. So if x is 0, there is no spring energy. We can kill that one off. Okay. Good to make eliminations. Makes the problem easier. Initially now, we look at the beginning of the problem. When the spring is compressed and the ball is sitting there, do we have any kinetic energy? No, the spring has not released yet, right? So we are sitting with no kinetic energy, just like before. How about gravitational? Yes, we have a height. So we will have mg y initial. How about a spring? Yes, we have a spring in this one. This will be 1/2 k x initial squared. Okay, so we have our spring. It's compressed, that's why we have an x in this one. We definitely have a y because there's a y value associated with that position. Okay, things are now in place. This is what we're trying to solve for is VF. Let's see if we have all the information we need. We'll have 1/2 times the mass, 0.035, VF squared. This is what we're looking for. Equals to, again, the mass, 0.035. G is going to be 9.8. And again, just like before, this is a negative 0.12. Okay. All right. Plus, I can probably add it on here this time, plus 1/2. The K constant. Ooh, good thing we solved for that. 954. And the x squared, again, the initial x, that needs to be squared. Okay. Well, looks like we have all numbers except for the V final squared. So let's go ahead, let's solve for it. Let's take 1/2 times the 0.035. That'll narrow us down to 0.0175 VF squared. That's equal to 0.04. Okay, same number as before, 0.04, negative. And then we have to add in this new one. So we've got 0.5 times our spring constant, 954, times this negative 0.12 squared. Gives us 6.8688. I'm gonna leave it out. We don't always have to round. Okay, now I'm trying to solve for VF. So let me go ahead and minus these two off. Get a number, and then let's divide that number. So I will have VF squared is equal to 6.8288 divided by this 0.0175. And then I will take a square root on both sides of that, and that should get me my answer. And we get then a V final of around 19.75. Okay, 19.75. So there we go. That's not bad. That's roughly a decent velocity. We're not talking thousands or millions of meters per second, and it's not zero and it's not negative. So that sounds pretty good. 19.75 meters per second for the initial launch of the spring. Okay, so you see kind of how these go, I hope. You can pick your points. You're free to pick where you want the energy final and the energy initial to be. Pick points that make sense with your problem so that they have the variables that you're looking for. List out all of the energies, simplify it down into just the energies that are relevant and important, and then just work through the algebra. Okay. All right, hopefully that worked out for example 1. Let's move on to another. Okay, so for example 2, it looks similar to what we already had. In the last one, we have a block. It's being pushed by 12 newtons. That mass is 6 kilograms. It's initially not moving. Velocity is 0. And we're looking again for what is the final velocity. But this time, we have some friction that is involved in that. So we have to ask ourselves the same questions. We know it's an energy problem because we've done these enough before now. We know it's an energy. And we have to ask ourselves, is that energy conserved or not? Okay. And in this one, being there's friction, it is not conserved, which means the change in energy is not going to be 0. Some of it is going to be lost, which means I cannot use E final is equal to E initial. That does not happen. I cannot equal that because I've lost some, okay, in the translation. So what I like to do with these is I like to look at the the energy and figure out where exactly it has gone. I kind of do them as work being the change in energy. So if I look at the equation for work, and we're going to use the force change in R cos theta equation, I want to look and see what is doing work, right? We're doing work by pushing the box, all right? So that's one thing. We are pushing the box. So let me look at that. I'll call that the, work done by you, okay? We'll look at that. Work done by you. How much work are you doing? Well, you're putting in 12 newtons of force. You're pushing the box 3 meters. And you're pushing it straight, horizontally. You're pushing that box for 3 meters, which means we're going to have a cosine of 0, which is just 1. So you're putting in 36 joules of work. But that amount of energy is not conserved. You're losing some of it. Right? So how much are you losing? Well, they call that a non-conservative work. Right? It's the work that's being done that you cannot get back. It's not conserved. So we call it NC. What force is causing that non-conservative work? The friction force. Right? The friction force. That friction force also acts on it with a delta R and cosine of theta. So let me see what that is. So WNC. Friction force. What is friction force? Well, we have an equation for it. It's mu times the normal force times the change in R. What's the change in R? 3. And then what's the cosine? So again, this is the angle between this and this. How do I know what the angle between the friction force and the change in R is? Well, for that, we might have to draw up a free body diagram. Okay, so here's our box. We are pushing with 12 newtons of force. There's the gravitational force. There's the normal force. And friction always works against the direction of travel. So it goes in the opposite direction. So the friction force is pointed to the left, right? The box is moving to the right. One is in the left, one is in the right. What then is the angle? It's 180 degrees. Okay? Now, what else do I know here? I know mu, that was 0.015, but I need the normal force in order for friction to take effect. What's the normal force? Well, I come on over here and I sum up everything that's happening in the x, I sum up everything that's happening in the y. Okay. And we see what's going on. In the y direction is my normal force. Okay. And I ask myself the same questions as I usually do. Is the box jumping up and down in the y direction? And the answer is no. Do I care what's going on in the fx direction? Not so much. I can do something like this. I can put 12 minus the friction force. But what I really want is the y, because I want the normal force. So in here we have normal force minus Fg, or mg. Okay, and then I get that the normal force is then equal to mg, okay, gravitational force. I can then take and plug that into my equation over here. And that'll give me the amount of work that is done by non-conservative forces of 0.15 times Fn. Fn is mg, which means my mass will be 6. G will be 9.8. Okay, so this is m and g. I then have 3, and the cosine of 180 is a -1. Okay, so those are just numbers. We can go ahead and punch those into our calculator here. 0.15 times 6 times 9.8 times 3 times a negative 1 gives us a negative, work done by non-conservatives, gives us a negative 26.46 joules. All right, so you might be wondering, where are we going with all this? What's happening here? I'm looking at the difference in work, because work is energy. So the change in energy, change in work, it's all related. How much energy did we put in? We put in 36 joules of energy. How much energy did we lose due to that friction? We lost 26.46 joules of energy. Okay, so we've got some leftover energy. We put in 36. So let's see. So we put in change in energy that is left would be 36 minus 26.46. Okay, and what do we get there? It means that we have 9.54 joules of energy left over. Where did that energy go? Friction didn't take it. We put it in. Friction didn't take it because friction is accounted for here. The rest of that energy had to go somewhere. And where did it go? It went into velocity. It went into a change in kinetic energy because, again, there was no Y. There was no spring. The only energy it could have went to is kinetic energy. So that means that we have work is equal then to E final minus E initial. And we know that it's not zero. E final does not equal E initial. So this has to be the change, overall change in energy, right? So this is the change in energy. E final, what was happening in the final for energy? The only one we have is kinetic energy. So we're going to have 1/2 mv final squared minus the initial, which was 1/2 mv initial squared. But the initial velocity was 0. So this whole thing is going to go to 0. How much energy do we have to work with, right? So this is the leftover energy. How much energy do we have left over? We put in 36. We took 26.48 out for friction. This left over 9.54 joules of energy. That is equal to 1/2 mvf squared. The mass again is 6. The velocity gets squared. So now we can take, and we can go ahead and plug that in and get an answer. We have 9.54 divided by 3. And then we need to take a square root of that. Okay, hopefully we've done this enough times. And we get a V final of 1.8 meters per second. Now you'll notice that's a lot slower than before in the last chapter when we looked at it, because there was no friction. Okay, there was no friction in the last chapter. Now we have added friction, so of course it's going slower. Friction is slowing it down. So these ones are a bit more involved. That's why they're in this chapter. What I like to do is look at the amount of work. Look at the energy that you put in to the system and how much of it did you lose to these non-conservative forces. That will give you a leftover amount. That leftover amount has to account for whatever the energy changed to. Okay, it gives you the leftover change of energy. Leftover change of energy can be put into kinetic, like here it's moving, right? It can be put into kinetics. It could be height of something. It could be compressing a spring. It could be any of the energies. Okay, but the point here is we need to find how much energy we have to work with. How much energy is left over once you take out the non-conservatives. Okay, let's look at another example. Example 3, let's do another one of these, this time with a spring. Where we're going between frictionless and friction. So here we have a spring with a block that has been compressed It has been compressed back 0.02 meters. There is a K constant on that spring of 1,000 newtons per meter. And no mass, right? We aren't given a mass. We don't know what the mass is. But question A states, if the surface is frictionless, and there would be a surface going across here, what is the speed of the block as it passes x equal to 0? So again, I'm putting up less and less on the board because you got to kind of picture these on your own and see what's happening. As we pull the block back and we're compressed here waiting to release, the velocity is 0. As soon as we release the block will begin to move forward because of the spring being compressed. It'll move forward to a point where it is over here, and the spring is now behind it at the point of x equals 0. Okay, so that's where we're at. And it will be moving, obviously. Okay, it'll have to be moving. So how do we tackle this? Okay. Well, the first one is, I think, the easier one because it's frictionless. Anytime you don't have friction, it seems to be easier. If there's no friction, we can jump into our conservation of energy equation, which just says the final is equal to the initial. Then we look at what energies we have. Okay. Well, there's only 3 right now. So what energies do we have? In the end is always where we start with, is the end point, the final stage. Do we have kinetic energy? Yes, we are, of course, going to be moving when that block flies through the x equals 0 point. That block will be moving. We will have a 1/2 mv final squared. Okay. Is there gravity involved? No. Is there a spring involved in the endpoint? Well, yes, there's a spring involved, but x will be equal to 0 at that point. So that also goes to 0. Okay. How about the initial? Okay. When the spring is pulled back and we are waiting to release, is there any kinetic energy? No. Velocity is 0 at that stage. Is there a change in gravity? No. There's no change in y. There's no gravity potential. Is there a spring involved? Yes. Is there an x for the spring? Yes. Okay, and that's going to be 1/2 kx squared. Okay. Now 1/2 and 1/2 are going to cancel out because they're the same on each of the sides. Okay. So I can actually kill those off as well. And I'm going to have m vf squared is equal to kx squared. And it told me the k was 1,000. The x squared, it doesn't matter if we go left or right because it's going to get squared anyway. So I'm just going to put it as a 0.02 squared because once it's squared, it's going to go positive. And I'm pretty sure I forgot to put a mass in here. I did. The mass is supposed to be 1.6 kilograms. So what happens when you do practice problems sometimes, you're making things up as you go. You have to add back in those details. Apologies. But there should be a mass of 1.6 kilograms for that block. You can't solve it without it. So 1.6 kilograms will get added in. And now all we have to do is just find out what that final velocity is. Okay. So pretty easy on this one. We're going to have 1,000 times that 0.02 squared. And then we'll divide over our 1.6 and then take a square root of our final answer. And we should get a final velocity here of 1.58. Yeah, 1.58 meters per second. Okay, so hopefully that's what we got. Let's go over here and let's say, if frictionless, what's the speed of the block? V is equal to 1.58 meters per second. So that's for part A. For part B, it says, well, now we have added friction. How is that going to change things? Okay, so now that we've added friction force of 4 newtons, do you think the block is going to be going faster or slower? Well, it should be going slower, right, with friction being involved. If there's friction, I can no longer use my energy conservation, so I need to kill that, get rid of it. And instead, what am I looking at? Well, I want the total energy, okay, the energy that went into it, and then I want to figure out how much energy is lost due to non-conservative forces, like friction. Find the difference, and then from that, I should be able to go ahead and find the velocity. Okay. So here I got to see how much energy total is put into the entire system, right? So let's look at energy or work total, right? The amount of energy input, right? So this is the energy that instead of us putting it in, it's the spring putting it in, right? The spring is the thing that's going to kick everything off and give the energy into the system. So what is the spring energy? Well, that's 1/2 kx squared. Okay. Now, if you want to think of us initially pushing the spring in, giving it the energy, like we're giving it the energy, we're loading the spring, you can do that, that's fine. The initial is going to be 0, the final is going to be the state that is just pushed in. So in reality, this ends up being the same equation. It's fine. What do we have for this? We have 1/2 the k constant of 1,000 and x squared being 0.02 squared. So this is the total amount of starting energy or starting work. So we have 0.5 times 1,000 times 0.02 squared. This gives us not much energy, but it gives us 0.2 joules of energy to start with. Okay. Now we got to figure out how much of that is lost due to friction. Or I guess NC is what they call it in your book. I should probably keep up with this. Non-conservative work. And what's that going to be? Well, that's the friction force. Okay. That is the friction force. How much friction took energy out. So you'll notice for the top one, I didn't use FR cos theta because it's the spring. I didn't have force in that one, so I had to use the spring as the internal rather than the acting force. For non-conservative force, we're going to go ahead and use friction force because that's the thing that's taking energy out. Friction force we know is going to be mu times the normal force, but we don't actually even need it on this one. The problem itself stated that the friction force is 4 newtons. So this is the friction force. We can say that it's 4 newtons. What's the change in R? How far does the friction force take effect? Well, we're only concerned between this point and x equals 0. So the distance that it's going to travel is 0.02. And of course, what's the cosine of the angle? Friction always works against you. So that friction force is going to have a cosine of 180. All right. What does that give us? That means that we are going to lose 0.08 joules of energy lost due to the friction force. Okay, so how much do we have to work with? What's the total change in energy beside, when you take into effect those two forces? Well, we have, or those two other energies. So we start off with 0.2. We lose 0.08. That leaves us with 0.12 joules of energy to use. Where did that go? It turned into kinetic energy. That's the change in energy. Change in energy would then be 1/2 mv final squared minus 1/2 mv initial squared. That's the change in the energy. Initially, it starts at rest. So that goes to 0. All we're concerned here is what is that final speed? All right, so we're going to have 0.12 is equal to 1/2 the mass, 1.6, mv final squared. Now we go ahead and we solve out again for v final, and we hope that it is less than the 1.58, because that would mean we're at least on the right track. So let's take 0.12. Let's divide it by 0.8, because that would be the 1/2 times 1.6. That gives us a 0.15. Let's take the square root of that, and that gives us a very slow velocity. That is 0.3. We're going to round to 9 meters per second. Now, does it make sense that it is going slower with friction? Of course, it means it's going slower with friction. Our velocity over here is now 0.39 meters per second. Okay, cool. So there's one example with a spring, friction, without friction, how to do it both ways, using conservation of energy, and then also using the energy and finding out how much is lost and what the remaining energy is doing. So that should give you a good example of energy conservation and work energy theorem. All right, let's do an example here on power. So for this one here, I got the power equations written up. Power is energy over time. You can also look at it force times velocity. And then there's a conversion of 1 horsepower is 746 watts. So this is the unit of power. The US unit of power is horsepower. Question states, how many horsepower would be needed? How many horsepower would be needed to bring a 1,400 kilogram car from rest to 45 miles per hour, which is about 20.1 meters per second, in 11 seconds of time? Okay. So for this, I'm looking for horsepower, which means I'm going to have to do a conversion from horsepower to watts, which means I'm really looking for watts. Watts is the unit for power. So I want power, and I was given time. So this first equation should be the one that I'm looking for. Power is equal to change in energy over the change in time. I want watts. I know that this took place in 11 seconds, so I'm looking for the change in energy. What energy changed here? Right? I went from rest to speeding. Okay, so the change in energy is kinetic energy. So I'm going to have 1/2 mv final squared. Now the initial speed, it said I started from rest, so I'm not even going to put it in because it's going to be a -0. Over the change in time was 11 seconds. Okay, so how much power then? I will have P is equal to 1/2 mass of the car, 1,400. Final speed, we've already got a conversion that happened in the problem, so that's nice, 20.1. That gets squared, and then that's divided by 11. All right, we grab a calculator and we look for power. So we'll have 1/2 times 1,400 times 20.1 squared, and the whole thing gets divided by 11. We're looking for 25,700 and we'll go 10 watts. But that's not quite my answer yet. That's in watts. I need to do a conversion to get it into horsepower, right? So go way back, do your conversions. You're going to need to multiply this by something with watts in the bottom and horsepower up top, and that's how you'll get horsepower out of it. Okay, so that should be pretty much pretty basic right now. What we want to do then is divide this by 746, because 1 horsepower, 746 watts. So we're dividing by 746, and we get something that's around 34.5 horsepower. 34.5 horsepower. Now this is a light car, 1,400 kilograms. It's only to 45 miles an hour. It takes 11 seconds to get there. This is definitely not a high performance vehicle. But it's interesting that the power is actually so low, 34 horsepower. Lawnmowers can go up to 20, 25, 30 horsepower. And there's actually a piece on there that is governed so that they won't go fast. If you're curious about that, look up lawnmower racing, where people remove those restrictions, and you can have some very, very fast lawnmowers. You can also have some fun with this, right? Do you want to compare your car, your personal car, or your parents' car, or your friend's car? You can easily look these up and find out what the horsepower is of their car. And then you can compare it to other cars, and you get a little better idea on where you stand. um, Horsepower is very, very small, 34.5 just for this little tiny car. So maybe this is a smart car like we saw in the video. All right, let's do another problem. All right, so for this one, example 5, we're going to have a light bulb. If you leave a 100-watt light bulb, and say you go into a room or something and you turn the lights on, you forget to turn them back off. Let's say you leave them on for 2 weeks. So you've left this 100-watt light bulb on for 2 weeks. How much energy is used? Okay, how much energy did that light bulb use? And electricity costs money. How much electricity, if electricity costs 40 cents per kilowatt hour, how much did it just cost you to leave that on for 2 weeks? Okay. So for these ones, okay, it is giving us the power. It's a 100-watt light bulb. So it gives us what the power is. So in this one, I want to use, and then it gave us 2 weeks, it gave us a time frame. So again, I want to use the power, change in energy over change in time. It gave us the power of 100 watts. The change in energy would be how much energy we spent in this amount of time. Well, how long is 2 weeks? Remember, I have to have SI units here. Okay. So finding 2 weeks in seconds. Oof, this one might be fun. All right, so 2 weeks would be 14 days. Okay. 14 days means every 1 day is 24 hours. Every hour contains 3,600 seconds. So now hours and days cancel, and this will give us how many seconds are in 14 days. So 14 times 24 times 3,600 gives us a lot. 1,209,600 seconds. That's the amount of time that passes in 2 weeks. All right, so I need to multiply that over to the other side. Okay, multiply by 100. It's just now going to be 120. 120,960,000. 120 billion, 960 million joules is the amount of energy that you spent on your light bulb that you forgot about for 2 weeks. So that's part A. Part B says, how much is this thing going to cost you? That's a giant number, but how much cost is this? If it costs 40 cents per kilowatt hour, how much did it cost you? Well, we have joules, but we don't have kilowatt hour. Okay, so there's a conversion for kilowatt hour. 1 kilowatt hour is equal to 3.6 times 10 to the 6th joules. So we do another conversion on this. Right? If we have this amount of joules, you're going to want joules in the bottom. You're going to want kilowatt hours in the top. and which just means you're going to divide your answer by 3.6 times 10 to the 6th. Now you can add in the zeros if you want. You can use it on your calculator by putting in the e function, or you can multiply by 10 to that power. You will get that you used 33.6 kilowatt hours by leaving that light on. Okay, but that's not our answer yet. Don't box that. You've used that many kilowatt hours. How much did it cost you is the question. Okay. It costs you 40 cents per kilowatt hour. Okay. You've used 33.6 multiplied by 0.4. And by forgetting that light on in that downstairs or upstairs or wherever it is for 2 weeks, you are getting charged $13 on your electric bill by having that light on. Okay. Something like that anyway. That's probably a little high for electricity there. But something like that could be in the near future anyway, with power and everything the way it is. And that's just a light. Some of your electronic devices, like your laptop, probably has a 400 watt charger in the new modern gaming laptops and whatnot. So you could have something that's a very higher consumption. Okay. This is how they determine when you go to buy something like if you're ever going to get a house and move in and you need to replace the refrigerator or the dishwasher or the washing machine or something. The energy efficient sticker that's on those will tell you what your yearly cost to run is, an average yearly cost. And that's how they calculate this. They run that thing for average use for a year, and it will tell you roughly how much it will cost you to run that appliance for a year on average. It's very broad, but that's how those things are kind of done. All right, we're going to do one more example, and then we'll call it for this chapter. Okay. So for our last example 6 here, I want to make sure we hit that other part of power as well. Then we've done examples with all of the new equations. So in this one, we have a force that's being applied to an object. Doesn't state what it is, doesn't really matter, but it's a force that's being applied to an object. That force is given as a vector, 30I hat minus 2J hat. And that would be in newtons. The object moves, get rid of this. This is in newtons. The object moves with a velocity of 6 meters per second in the x direction. What is the power output? Well, okay, I've got a vector here, which leads me to believe that we've got this, but I don't have a vector for v. But I know that there's no energy, there's no time involved in this. So it's going to have to be the other equation. Okay, which means we'll have P, put it over here, means that we will have P is equal to F dotted with V. So I'm going to have to run this. So I have a dot product. Okay, so the way I like to do dot products, put them one over the other. Now I have my force, that one's easy, it's a 30I minus 2J. For the velocity vector, just remember back to vectors and how we go about these. This says that it has a magnitude of 6 meters per second, but it tells you that it's in the x direction. Okay, so even though it didn't give you an angle or anything there, it states that it's in the x direction, which means it's only going to be in the I hat direction. Which means there is no component that's in the j. All right, I can do that as a plus. No component that's in the j. And then again, when we do dot products, we have to look at like-minded, like directional vectors. So that's why I write them one over the other, so I can just multiply down. And I'm going to end up with 30 times 6, which is going to give me P, which is these two. 30 times 6, which will give me 180. And then I times I is going to be a 1. I have negative 2 times 0, which gives me a 0. J times j is 1, but 0 times anything is 0, which ends up being 180 watts of power. Okay. So these ones are usually a bit simpler with the dot products. It's just knowing what you're doing with the dot product that makes the difference and makes the problem a little easier. Okay. All right, I'm going to end that one here and do the homeworks, do the other examples that we have, and meet me on the next chapter, chapter 9.